So in part 2 of this course, we'll talk about some basic concepts of probability theory. So some general definition of probability theory here, some most basic concepts including some random experiments. Whenever you do some probability-related studies, you carry out some random experiments. That's basically a mechanism to produce a definite outcome that cannot be predicted with certainty. So every time there is a randomness there. If there is certainty involved, then it's not a random experiment anymore. And the random space or sample space associated with a random experiment is a set of all possible outcomes. For example, the one to the right here. So you have two slides, or you can simply consider this a boy and girls when you give a birth to a child. So you have a boy, girls every time. You consider you have first time, you give a boy and girl, you have 1/2 chance for getting each. And then you have another boy or girl, you have a second child, then you have equal chance to get boy and girl in both cases. So every time you have random experiment set, and then you have a total possible outcome with this. Consider you have 3 children, then you have all the possible outcomes joined to the right here with a BBB, boy, 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 all the way down to girl, girl, girl. And then you have all the possible 8 combinations. So an event is a subset of the sample space. And for a particular event, it will be a subset of what could be happening. And if you're given 2 boys and 1 girl, and for example, you want to study the possibility when you have 1 girl and 2 boys, then you have a subset of that. You could have a 1 girl and 2 boys, and you have a BGB is a one possible combination, and a GBB or another one, or BBG. There could be 3 possible combinations to satisfy your requirements. So that's an event. It's a subset of the sample space. So talking about probability, you can talk about probability of an outcome. Basically, if some number is between 0 and 1, it measures the likelihood of the single trial. So you give something a trial, you have a chance to get something out, then this probability is measured by whatever the times something happening divided by whatever the total possible combination could be. So another probability is about probability of an event. Probability of an event, because as we talked previously, an event is a combination of multiple possible cases. And depending on how you describe the event, the event could be simply subspace of all the sample space you might have. So for example, A is probably describes certain event, that event 1 and event 2 will be happening. And B is including possible cases when event 2, 3, or 4 could be happening. The probability for A to happen is simply the probability for event A to happen plus the probability for event 2 to happen if they are completely independent and independent outcomes. The same goes for B. You have the probability for B to happen is simply the probability for event 2 to happen plus probability for event 3 to happen and event 4 plus 4 to happen. So P2 plus P3 plus P4. So this is straightforward because all your event here, not event, probably I would say an outcome here. E here representing an outcome, and PA, PB are the probability for 2 events. If the collection of all outcomes that are events of both events A and event B, then you are simply trying to figure out what's possible for both A and B, for the events in the cases for event B and A happen. So for example, in the sample space for the total dice you roll, you have total 6 possible sample outcomes. And if A is an event defined as a number of odd numbers, and B is a number less than 3. So for A to happen, then you have possibly 3 possibilities. Basically, you have 1, 3, and 5. And B is a number less than 3, you have 1 and 2 possibilities. So you can do this simply by looking at the possible outcome for both A and B. Then you divide the whole thing by the total possibility. So what's the probability for intersection of A and B? So A is simply 1/2 because it's just the number of rows to be all divided by total possible combinations, 6. So you'll be 3 by 6, you get 1/2. B is a number less than 3, you have 1 and 2, you have 2 possible outcomes. divided by total 6 space, sample space, you have 1/3. So P and B, A and B is simply 1/2 times 1/3, which is 1/6. Complement of an event is the connection of all outcomes in a sample space that are not elements of the event. So it's kind of like the inverse if you think about it the other way. Consider the sample space S is 1 all the way to 6. If A is an event, that the number road is odd. So the A complete is simply 2, 4, 6. Because those are the elements that contain in A, but it's in the rest of the sample space. So what's the probability of the event? The number road is even. It's simply 1 minus 1/2, it's 1/2. So this one is relatively easy. You find something to happening, and the chance for the rest to happen will be just 1 minus the chance for the event A to happen. For independent events, for both A and B to happening, then it's simply for A to happening times for B to happening. It's so-called multiply rule, if you still remember what you learned in high school or even mostly I think AP maths, you probably have learned that. So for the likelihood of both A and B occurring, it's simply PA and B, but now PA and PB are independent measurements. So PA is the probability for observing A, and PB is a probability of observing B independently of each other. So, for example, for the sample space S, it goes from 1 all the way to 6. If A is a number rolled in odd, it's odd, so what's the probability for A? It will be simply the 3 numbers divided by totally 6 numbers, you get 1/2. And B is a number less than 3, it's simply 2, 1 and 2, those are 2 numbers divided by 6, that's 1/3. So if A and B independent, so they are simply ruled independently, so PA and PB is simply 1/2 times 1/3 is 1/6. So here comes another possible scenarios that it's called a union of events, which means the connection of all outcomes that are elements of one or the other of the sets, or both of them. If you do the A union B, it will be simply PA plus PB minus PA and B, right? So if you look at the total area, it's simply A plus B minus whatever in between A and B. And for example, if you are trying to calculate in the sample space S, which goes from 1 to 6, if A is a number rolled is odd, B is a number less than 3, what's the probability of the union A and B? Okay, for A is number rolled is odd, is simply what? It's 1/2, right? We already calculated that. B is simply 1/3, we also calculated that. But now, if you simply do A plus B, it will be, or PA plus PB, it will be 5/6. And then PA and B is what? It's simply 1/6. So you subtract that from the PA plus PB, you get 4 divided by 6, which is 2/3, to 2/3. So a total probability for A or B to happen. The reason that you need to consider this extra PA and B because you overcounted that once by doing PA plus PB, you overcounted that particular outcome. You need to subtract that outcome. So that's a PA union B, you get PA plus PB minus PA intersect B. Another commonly used probability is called a conditional probability. This actually is closely linked to the Bayesian theorem, and we'll talk a little bit later. So what it says that PA B here, it's the likelihood of A occurring, given that B is 2. When P and B are not relevant, so this one it's not, it's simply A, because A and B are not relevant, no matter B is 2 or not. PA bar B is simply PA. So nothing to worry. But now, when P and B are relevant to each other, probably A is depending on B and B depending on A, since will be different. Because there are some outcomes between A and B that are overlapping, that are intersecting. So when B is 2, it's likely that A will be changed. So you need to calculate that based on this formulation. So the PA when B is 2 is equal to the PA and B intersect B divided by PB. So A and B is the likelihood of both A and B are occurring. That's the possibility. And the PA and PB are just probability of A and B independent of each other. It doesn't really consider A when calculated B, then PB is a value for that. So for example, if I look into the sample space, again, S goes all the way from 1 to 6. If A is a number road is odd, which is 1, 3, 5, and B is a number less than 3, which is 1 and 2. Now, look at A union B. So 1, 3, 5, and 1, 2. There is a 1 number, 1 here. 1 shows in both A and B. So that's the intersect A and B. Now P1, because intersect A and B is just 1. That gives you a probability of 1/6. Divide by PB give you 1/2. The reason is that for it will be 1/2 mainly because B has only 2 values, 1 and 2, right? For 1 to happen, assuming you observed B when B is 1, that A will be 100% be there. But now, if your B is if the B value is 2, then A cannot be showing up. The probability of A bar B will be 0 because there's no value, no outcome in this event A when the B is 2 here, because there's no outcome in event A. So in that case, PAB will simply be 0. Now, if you consider all the possibilities, whenever B happening, so you have a 1/2 chance for PA bar B to happen, because B itself could be 1, could be 2, and A could be happening if B is 2, and that's 1/2 chance. So that's why we got 1/2 for the value. You can do this calculation directly by plugging the values for P and B and PB separately. You can see it's 1/6 divided by 1/3, that's 1/2, which completely makes sense here. So Bayesian theorem is more or less like that, but it's a bit more involved to consider different conditions. By not simply consider the PA and B, and it's just PBA and times PB will be PA and B from that perspective. So the likelihood of A occurring given the B occurring is PA bar B, and the opposite, the likelihood of B occurring given that A occurring is PB bar A. As we explained previously, these two are different. So PA and PB are probability of observing A and B independently. And P union B is equal to PB union A. I'm sorry, union. It's an intercept B and B intercept A, because you can see whenever they have intersection between two sets, no matter which direction they are, you are manipulating, you are doing the calculation, they are the same. So what Bayes' theorem tells us that the probability of A to occur when B is 2 could be calculated based on the probability of B independently, and also probability of A independently, and probability of B to happen when A is 2. So this gives us a good way to estimate something cannot be easily calculated, observed. And this could be used to do a lot of probability analysis and used in many machine learning models. One of the most famous ones is so-called Bayesian method. It's actually using this Bayes theorem to figure out the spam, doing the spam filtering and many other classification problems.